Welcome to the Deep Dive, where we sift through the sources, really pull out those vital nuggets of knowledge, and hopefully spark some aha moments for you all without, the usual information overload. Okay, let's unpack this. Today, we're plunging into the core principles of modern application delivery. And our source material, it's a little unconventional, actually. We're using practice questions for the 6V0-22.25 exam, which focuses on the AVI platform. Now, before you start thinking flashcards and cramming sessions, think of these questions less like a test and more like really well-crafted prompts. They're surprisingly effective at distilling some pretty complex architectural and operational ideas into, clearer insights. Think of them as signposts, maybe, guiding us through application services.
Yeah, and what's really illuminating here is how these, seemingly technical questions, they actually reveal fundamental principles, stuff that's critical for anyone managing digital services today. We're talking load balancing, resilience, performance management, scaling, the whole package. Our mission isn't just like finding the right answer on a multiple choice list. It's about peeling back the layers, understanding the why behind these solutions. What's the strategic value? And maybe most importantly, what does it all mean for your applications?
Right. And just for a tiny bit of context, this exam, the 6V0-22.25, is typically around 90 minutes, maybe 65 questions. But honestly, we're leaving the test anxiety behind. We're just using these questions as a launch pad. Way to understand the brain, the muscles, maybe even the nervous system of really robust, intelligent application delivery. We want deep understanding, not just memorization. So if we're building the system, where do we even start? We need some kind of central command, right? Let's think about the brain of the operation, centralized control.
Yeah.
I mean, in any complex system, managing every little piece individually, that's just a nightmare. So the challenge for platforms like AVI is, how do you get consistent control, deep visibility, and automation across, potentially hundreds or thousands of applications? The practice questions get straight to it. Something like, which component of the AVI platform is responsible for centralized management, control plane, and analytics? You get the idea. And while you might see options like Service Engine or Virtual Service, the real core, the central intelligence, that's the AVI controller.
Precisely. The AVI controller, it's not just some management dashboard. It really is the strategic command center, the actual brain of the whole thing. And what's insightful isn't just, the simplicity of having one interface. It's how this central control plane enables policy-driven automation. Across your entire setup, it kind of shifts the focus. Instead of manually tweaking individual load balancers, you define the desired behavior at a higher level. You tell the controller what you want, performance goals, security rules, how resilient it needs to be, and it handles orchestrating all the service engines and virtual services. This fundamentally changes the game for big deployments. It makes consistency and automation just built in, frees up engineers too.
Okay, that makes a lot of sense. A single brain directing everything.
Yeah.
But doesn't that raise a question? If everything relies on this one brain, isn't that a potential single point of failure? Or maybe a bottleneck if things get really huge?
Yeah.
How does AVI make sure the controller itself is, resilient enough?
That's a really excellent point. And yeah, it's a critical design thought.
Yeah.
So while the controller is the single point for management and configuration, it's designed for high availability. It uses a clustered architecture.
Yeah.
Typically, you deploy, say, 3 controller nodes, active standby or even active. If one fails, another just takes over seamlessly. And crucially, the data plane where the actual application traffic flows that's handled by the service engines, and they operate independently once they're configured.
Oh, okay.
So even if the controllers were to temporarily go offline, your apps keep serving traffic. No interruption.
Right.
The controller cluster mainly affects management access and maybe analytics, but not the live traffic itself.
Fantastic. Okay, so we've got our resilient brain, the controller, handling the big strategy and policy.
Yeah.
Now, how do we actually get user requests to the application? How does that traffic flow? This gets into the building blocks of traffic delivery. When you set up a new app, you need to tell the system, okay, here's how it looks to the outside world, and here's where the actual servers are. So a core question might be something like, when configuring a new virtual service for an HTTP app, what object defines the back-end servers? And sure, there are other bits like application profiles, but the absolute foundation you need. It's a pool.
A pool is absolutely foundational. It's where the rubber meets the road, really.
Right.
Think of the virtual service. That's like the public face, the address users hit. But it doesn't host the app itself. It needs to know where to send the traffic. And that's exactly what the pool does. It defines that collection of actual back-end servers. And it's not just a simple list either. Inside the pool, you set up crucial things like health monitors or the servers alive, and the load balancing method you want to use. Without a pool, your virtual service has nowhere to send the traffic, no muscles to do the work, It's the critical link.
That paints a really clear picture of how those pieces fit. But, applications aren't all the same, are they? Some have specific needs, like keeping a user tied to one server for their session, or maybe they use unique headers for authentication. So once traffic hits that virtual service and it's heading towards a pool, how do you handle those application-specific details, the network-level stuff? This is where the practice questions bring in another key component, like you're setting up an app using a custom HTTP header for session persistence. What component lets you do this? And this points directly to the application profile.
Yeah, the application profile is incredibly powerful. It lets you sculpt and optimize traffic right at the application layer. Often takes load off your backend servers too. It's like the Swiss Army knife for how the virtual service interacts with your app's specific needs. So yeah, custom header persistence, super important for things like shopping carts, right, where the user needs to stick to the same server.
Absolutely.
But application profiles do way more. You can set up complex content switching based on URLs, apply WF policies, web application firewall for security, or even do granular rate limiting, protects your backends. It allows for really tailored behavior. It's much more intelligent than just basic traffic splitting.
Okay, so we've got the brain controller, the public face virtual service, the back-end muscles pools, and they're all fine-tuned with application profiles. But, well, the real world is messy. How do we keep things running smoothly, especially during maintenance or, when something just breaks? This brings us to ensuring resilience. And honestly, for anyone who's dreaded maintenance windows, this next idea is huge. How do you keep an app live even while you're updating its core parts? A question might ask. To ensure high availability during an upgrade, which upgrade method for service engines? And the answer everyone wants to hear, non-disruptive upgrade. The non-disruptive upgrade, that's a cornerstone of modern resilience. It's a big shift in thinking. Historically, upgrades meant downtime, period. With this method, the service engines, the part actually handling the traffic, they get upgraded in a rolling fashion. So imagine you have a group of them. Instead of taking them all down, you update one. Once it's back online, verified, then you do the next one, and so on.
And traffic just keeps flowing through the others. Exactly. Existing connections continue through the active engine, so you maintain high availability, prevent downtime during the upgrade. It's critical for important services. It really shows that resilience isn't just about bouncing back from failure. It's about building systems that keep going even during planned changes.
That's a massive win, updating without downtime. But what about the unexpected? What if a back-end server, one of those muscles in our pool, just suddenly dies and starts acting weird?
Yeah.
How does the system react fast enough to keep things working? This is where maybe the nervous system comes in. A typical question could be, when a health monitor marks a back-end server as down, what's the most immediate action the service engine takes? And the crucial immediate step is it stops sending new connections to that server.
That's right. It's a critical, instantaneous reaction. Think of health monitors like they're constantly checking the pulse of those back-end servers in the pool, the sensory nerves. The moment a monitor detects a problem, flags a server as down, the service engine immediately stops routing any new traffic to it.
Just cuts it off for new requests.
Yeah, exactly. It protects clients from hitting a dead end. Existing connections might time out or get shifted depending on the setup, but the key is stopping new problems instantly. It prevents one server failure from causing a wider outage.
Okay, speaking of intelligent reactions, let's talk about how traffic gets spread out to begin with, especially for apps that need consistency. This gets us into smart traffic routing, load balancing algorithms, persistence, all that good stuff. We know session persistence is vital for things like shopping carts or logins, right, where the user has to stay connected to the same backend. So a question might be, which load balancing algorithm is best for session persistence based on the client's IP address? And while there are options, the direct answer is often source IP address.
Yeah, the source IP address method is a classic, and for good reason. It does exactly what it says. Maps the same client IP to the same backend server consistently. Essential for apps that track state using the client IP. If you break that connection, the user's session gets disrupted.
Makes sense.
But it's not perfect, right? Like if you have tons of users behind one big corporate firewall or NAT gateway.
They all look like the same IP.
Exactly. So they might all get piled onto one back-end server, which isn't great for load balancing. So it highlights the strategic point. You need to understand these algorithms to pick the right one for your specific app and your users. Don't just default to, say, round robin if you need persistence.
Right, tailor it. Okay, so even with a great setup, smart algorithms, resilience, performance issues can still happen. Clients complain things are slow. Where do you look first? How do you quickly get a handle on what's really going on? That's a performance and proactive management. A key question here might be, when a client reports slow performance, where should an admin first look for a real-time view of latency, server response time, errors? And the most direct, useful place is the Virtual Services Analytics tab.
What's really game-changing about this is having integrated real-time analytics right there. It cuts through the noise. The Analytics tab on the virtual service gives you that immediate end-to-end view. Client latency, network latency, server response time, errors, throughput. It's all there.
So you can see the whole chain.
Precisely. It's designed to be the fastest way to figure out where the delay is happening is the user's network, the ADC itself, the backend server, the application code. It saves so much time compared to digging through separate logs or tools. You go from it's slow to here's why it's slow, much faster. It changes how you troubleshoot.
Okay, troubleshooting is one thing, but being proactive is even better, right? Especially with security. Certificates are a perfect example. Seems simple, but oh boy. An operational question might be, what's the primary task to ensure an SSL certificate doesn't expire and cause an outage? It sounds basic, but the answer is obviously renewing the certificate well before its expiration date. But it happens.
You're absolutely right. It seems obvious, but expired certificates cause major outages distressingly often. Admins have to proactively renew and replace those SSL certs on the virtual service before they expire. It keeps encrypted connections working, protects data, maintains trust. But it also points to a bigger idea. Security isn't a one-off task. It's ongoing. You neglect something seemingly small like certificate renewal, and the consequences can be huge. Outages, reputation damage.
Compliance issues, yeah.
Exactly. It's foundational for trust and keeping the service running securely. Non-negotiable these days.
Okay, final stretch. Let's talk growth. Apps aren't static. They need to scale, sometimes suddenly if something takes off. How do you efficiently scale up to handle more traffic without rebuilding everything or constant manual tweaking? This brings us to scaling and alerts. A key question here. What's the most efficient way to scale an existing application using Avi's elasticity features? If your app gets popular, you need this. The efficient answer, increasing the number of service engines within the service engine group.
Yeah, and this is where that true elasticity really shines. Scaling efficiently isn't just about having more servers ready. It's about the system intelligently managing that new capacity automatically. You just add more service engines to the group, the Avi controller detects them, configures them, starts spreading the load across them automatically.
With no complex manual steps.
Right. It handles much more traffic without you needing to manually reconfigure everything. That's a huge difference from traditional load balancers where adding capacity often means a lot of manual work. It makes you ask, how much effort does your current scaling process take? Can it adapt quickly? True elasticity is automated, intelligent adaptation.
And if these systems are scaling and adapting intelligently, how do they let us know when something actually needs our attention?
Yeah.
You can't just stare at a dashboard all day. So how does the system communicate effectively? A question might be, what is the primary purpose of an alert action in the Avi controller? The core idea is to specify the notification method when an alert is triggered, like email or SNMP.
This points out a really important difference. There's identifying an issue, and then there's effectively communicating it. An alert condition defines the problem like high CPU or a server failing health checks, but the alert action decides how you get notified. Is it an email to the on-call person? An SNMP trap, that's that standard network protocol going to your main monitoring system? Or maybe a webhook firing off to Slack or PagerDuty?
So you choose how you get the message.
Exactly. You tailor the notification to fit your team's workflow. Make sure the right people get the right info through the right channel at the right time.
As applications get more complex, more distributed, and users expect everything to be always on, how might understanding these principles, the architecture, the operations, empower you? Not just to manage things, but actually innovate, to future-proof how you deliver those digital experiences. Something to think about, maybe. How could these ideas reshape your approach? Anyway, thanks for joining us on this deep dive. We really hope it sparks some new ideas for you.